Welcome everyone. I am Noor Abdelmajid and I will present JenTab, matching tabular data to knowledge graphs. It's a joint effort with Zerko Schindler, University of Vienna, Germany. I would start with the Sem Tab challenge tasks, giving Wikidata as a target knowledge base. Here is the first task, cell entity assignment, or CEA. It assigns a cell value to an entity mention. The second task, CTA, or column type assignment, it associates a semantic type, like Wikidata identifier for country, to the highlighted column. The last task is CBA, or column property assignment. It generates a semantic property, like capital, to a column pair. The rest of the outlook will cover our preprocessing, assumptions and data sources, then the proposed approach, afterwards experiences and results, finally conclusions and future work. Our approach is retrieval and matching approach. Our target is to create as clean cell values as possible. So we have implemented 3 different steps of the preprocessing. At first, the generic fixing, then low-level type prediction, and finally the type-specific cleaning. The generic fixing includes data cleaning, like handling empty values, encoding fixes. We rely on fixed text for you library to fix such encoding errors, like the example of Tübingen. And finally, generic parsing, which aims at restoring missing spaces among words inside a given string. The second step is the low-level type prediction. We used regular expressions to distinguish among various types. The most important types are object columns. We create CA mappings for them. And the other important types are those who have Wikidata equivalent types like date, decimal, and quantity. One special case about object column: if we have classified a column as an object column, but it's not listed in the given targets, we handle it like a string property. Along with the others, all of them contribute towards creating the CPA task. The final step of the preprocessing is the type-specific cleaning. By this means, we can do further processing on cell values. For example, for quantity value, we extract the first number from a given string, like the distance value or the first date in a nested dates string. One more example about object cells, we also apply autocorrect on some misspelled words. Before explaining JenTab as a system, we mention our list of assumptions as well as our used data sources. We assume that all tables have a horizontal orientation, which means cells in one column belong to the same semantic type. Moreover, all cells in one row represent one subject entity classified as object, where the rest of cells are easier object or literal properties. The subject column is the first object column in a table. Our used data sources are only the publicly available Wikidata Lookup API and Sparkle endpoint. JenTab follows a CFS pattern. In the following slides, I will explain the pattern and its pipeline. The CFS term stands for Create, Filter, and Select. The figure represents the 3 stages of the approach. Each stage covers the 3 tasks jointly. The Create stage aims at generating as large pool of candidates as possible, where the Filter stage tries to reduce the generated candidate sets by using different contexts from other tasks. Finally, the Select stage which choose only one candidate from the remaining set for each task. Here, we reordered the developed building blocks in the previous slide into an order of execution or a pipeline. In general, it's divided into a core pipeline presented in the first group, filling missing mappings or gaps using various methods, like in group 2, 5, and 7. Finally, filter and accumulative selection, like in group 4, 6, 8, and the last resort in group 9. In any group with two building blocks do the same task, like for example in the first group, the last two methods aim at CA candidates filtering, we execute the second if and only if the first method failed to solve. Same is applied in group 4 and 9. The first group represents our core pipeline. It creates most of mappings for the three tasks. The first step tries to look up a given cell value using Wikidata labels. It relies only on cell values with no consideration of any semantic context. In create CTA, we retrieve semantic types of column, like for example the B31 and B279. Then we aggregate the results per column. Afterwards, we filter those types by calculating their frequencies and drop all types that are less than certain support by cells. The same filter affects the CA mappings as well, such that we remove CA candidates that have no CTA support anymore. In the following step, for each subject cell candidate, we retrieve its respective properties. We consider an object property match if its identifier is found for the object cell candidates. However, literal properties are even more challenging. We do not rely only on exact match, as we use the publicly live Wikidata resources, which differ from the used resources while creating the dataset. So we tolerate some margin in values like, for example, 10% of numbers. Another filter by using the raw context or the generated properties. In this case, we drop CA candidates that has no properties match in its row. Group 2 of our pipeline represents our first attempt to fill the missing CA mappings. It targets subject cells and uses both of row and column context to retrieve such missing mapping. As long as we keep track of CA candidates, if we found a change due to the execution of group 2, we need to rerun this part of the core pipeline. Before the first trial of candidate selection, we apply a more sophisticated filter function which keeps CA candidates with the most of property matches in its row and remove the others. After that, among candidates set for a given subject cell, we select the candidate with the nearest label using Levenshtein distance as a string similarity. However, for an object cell with no mappings, we try to look for the nearest value among its column and pick its solution. The next step involves selecting a CTA candidate, where our primary method is the least common subsumer, or in short, LCS. I will show you a tracing example for it in the next slide. Finally, we apply a majority vote on the generated CBA. Here is the LCS example. The table on the left shows the direct parents or P31 of given cell values, where on the right we have created a hierarchy of the retrieved parents. The LCS ensures the selection of the lowest parent with the highest cell coverage. We continue filling gaps for non-object cells by using group 5 and 7. At first, we try to retrieve all instances that are related to the type of the subject cells. Then we try to match the retrieved entities with the object cell and remove those that are too distant from the object cell value using the same string similarity. For group 7, the same style is applied, but using the subject cell candidate and its properties. For group 6 and 8, we recompute the CPA and apply the unmatched properties filter, then we apply a selection by the string similarity. Ties are broken using popularity. We define the popularity by the number of triples that this candidate appears in. Our last resort, or simply the guessing blocks, we assume that most of the targets are already solved. However, we try a couple of new selecting methods about CTA for the unsolved ones, which are direct parents, basically the same as we implemented in CTA generation, but excluding the parent of parent. Then we apply a majority vote on those. The other strategy uses popularity as a selection criterion. For the results, this table shows our scores from the leaderboard in the challenge rounds. Here we list our experiences from the challenge. Our choosing modular approach allowed us to experiment various methods, enable and disable some parts of our pipeline. So the explained building blocks are continuously evolved. For example, CBA wasn't implemented during round 1. We also faced different challenges. Spelling mistakes in datasets, for example, we experiment handling them in various trials. One more challenge is about using the live system from Wikidata. This will leave out some mappings unrecoverable. In summary, we introduced our system, JenTab. It matches table components to Wikidata knowledge base and purely relies on the publicly available Wikidata lookup and endpoint APIs. As well, we explained how it works using the CFS pattern. We see different ways to improve JenTab. First of all, increases the accuracy of low-level type prediction, especially about date type. The second point concerning the optimization of the expensive components, like computing the lookup of the auto-corrected values, require substantial resources. One more point about the performance of the endpoint service, rewriting some queries should be also considered. Last but not least, we would like to thank our supporters and we would like to thank you all for your attention.